Kuzuzangpo, Bhutan e-learning project welcomes you all to this lesson. I am Sushmika Tamang, and this is a physics lesson for Key Stage 5, that is classes 11 and 12. So today we are going to learn about quantum mechanics and specifically photoelectric effect. And the objectives for today's lessons are: explain the concept of photon, explain the photon model of light, study photoelectric effect, give a few applications of photoelectric effect. Okay, so before we go into photoelectric's concept, I will tell you a story about how this quantum mechanics started. So in 1900, light was known to people only as waves. During that time, a British scientist named Lord Rayleigh knew that the hot body gave different colors of light at different temperature. And to figure out how these colors came from an object at different temperature, he formulated a formula. And with his friend Jean, they considered a body called black object. Now this black body or black object is not considered like really black. Actually, it was considered to be an object which absorbed all the light that emitted on it, fell on it, without any reflection. And in the process, it gave out energy in the form of radiation. Now, in the real universe, there is no perfect black body, because there is no object that will completely absorb all the light and then give no reflection. But stars come close. Anyways, so this Jean and Rayleigh, they said that this black body had lots of vibrating oscillators, and then during the process of vibration, it gave out energy. And they came to the conclusion that higher the frequency, higher the energy or intensity. Now this was the problem, because you know the frequency of UV is really high, and if that frequency is reached, then the black body is going to give you intense amount of UV radiation and you're going to burn. For instance, if you're sitting near the fireplace, and then you will be burned by the intense energy of UV rays. Now, this was completely against the law of conservation of energy. And this was a monumental issue because it highlighted the flaw of classical physics. Now, the solution to this problem came accidentally from a man named Max Planck. He was actually hired by one company to design a bulb that would produce intense light, brightness, and not heat and UV radiation. And in the process, when he was doing the experiment to bring that kind of bulb, he found out that his experimental record was not matching the Rayleigh-Jean graph or the law. So in his experiment, he found that as the frequency increased, the intensity decreased. And that matched the real experiment. So he proposed one revolutionary idea. He said, what if the vibrating object or vibrating particle in the black body gave not continuous but discrete amount of energy in the form of packets? And that energy was represented by hf. F is the frequency of the light. H is a small amount, which later came to be known as Planck's constant. So that he proposed. Now, you know how difficult for us it is to accept the change. Same thing happened to him. Not many were convinced with his idea because it was revolutionary. And he himself, Max himself, was not much convinced because what he did was a solution to kind of math problem. So then he was hoping that his work may be refined with passage of time. But after 5 years, Albert Einstein came. And then he took the quantum theory of Planck's and explained photoelectric effect. Though it was explained by wave theory, but that failed. So he took this quantum theory from Planck's and explained photoelectric effect, saying that light here has to be considered as particle, which later came to known as photon. Now, same thing. His contemporaries were not happy with what he said because this idea was revolutionary. And so a person in particular, his name was Millikan, was infuriated with his idea. And then he said that this explanation of photoelectric effect is a piece of nonsense. So he wanted to prove Einstein wrong. So he conducted years of tedious experiment, and finally he actually succeeded in proving him right. And in the process, Millikan also found the accurate value of h, which is the Planck's constant. So then it was like his experiment was like experimental confirmation of Einstein's hypothesis. So for this explanation, for this photoelectric effect, Einstein won a Nobel Prize in physics in 1922. And even Millikan got a Nobel Prize in 1923 for his work. And this is how the revolutionary quantum mechanics gave its birth. Okay, so how was the story? And what is your takeaway from the story? For me, the takeaway is failures are good, actually. Had there been no failure of Rayleigh Jean law, which was actually called UV catastrophe, there wouldn't have been quantum mechanics. So failure is stepping stone. Another one I feel is that if you are right, then nobody can prove you wrong. Millikan tried to do that, but he finally ended up proving Einstein correct. Okay, now we will learn photoelectric effect. So you know that initially or previously in the 1900s, you knew light was only behaving as wave. Now we know that light is also behaving as particle. So this is called wave duality, wave-particle duality, which means light has both wave as well as particle nature. So two models of light are there. So wave model actually explains properties of light like refraction, reflection, diffraction, and all. Now, photon model is used to explain phenomena like photoelectric effect, Compton's effect, and so on. So today we will be specifically talking about photoelectric effect. Now, what is photoelectric effect? Now, photoelectric effect is the effect or is the phenomena where a light is falling on a metal surface, and in the process, the electrons, when light falls on the metal plate, the electrons are ejected from the metal plate. So that phenomena is called photoelectric effect. So ejection of the electron from a metal surface when high frequency light falls on it is called photoelectric effect. Now, this was though explained by the wave theory, but it had some failure. So here, the light is considered as packet of energy, photon of energy. So this particle, each packet is supposed to have energy which is equal to hf. H, as I said in the story, stands for Planck's constant, which is 6.63 times 10 to the power negative 34 joule second. So this is a constant value, and this times the frequency of the given light gives you the energy of a photon. So this photon falls on the surface of the metal. It gives out all its energy to one of the electrons. And this electron will take minimum energy, and that minimum energy is taken by the electron to eject out of the plate. So that minimum energy taken by the electron is called work function. And you should know for a given metal plate, work function is a constant value. Okay, so with that minimum energy, it has come out, and with the leftover energy, which is called the kinetic energy of the electron, it moves. So then, it is mathematically total energy of photon E is equal to work function, which is the minimum energy required by the electron to eject from the plate, plus the kinetic energy of the electron, photoelectron, with which it moves. So this together is called Einstein's photoelectric equation. Now we will learn about the failure of wave theory or classical physics to explain photoelectric effect. Now, before we go into the failure, what are the reasons of failure, we will learn or just slightly revisit electromagnetic spectrum, which you have already studied in lower classes. So electromagnetic spectrum, as you know, there will be visible light, and then you have the higher frequency, and towards the right you have the lower frequency or longer wavelength light. So here, all the light in the electromagnetic spectrum has the same speed as that of the speed of light, which is c is equal to f lambda. F is the frequency and lambda is the wavelength. So this is how you calculate the speed of light. And you also know that with the increase of frequency, there is increase in the energy, because energy of a photon is given by hf. E is equal to hf. So if f increases, the energy of the photon increases. So now we will get into the failure of wave theory to explain photoelectric effect. So here I am taking an analogy of waves, ocean waves or sea waves, to be the light waves, okay? And the beach balls are considered or taken as the electrons on the metal plate. So according to wave theory, frequency of any water waves, high frequency, low frequency, all could push away the beach balls that were lying on the dock. So it just means, according to wave theory, it means all frequency light could eject electron, but practically only high frequency light could eject electron, not frequency lower than, we call it threshold frequency, I'll talk about it later. Lower than threshold frequency, light could not eject electrons. So that was one failure. Now another analogy I'm going to take here, that is to do with the intensity. So again, if you look in the same analogy where you have the waves and the beach balls as the electrons, so you can see high waves means high amplitude. High amplitude means high intensity, because amplitude is directly related to intensity. So when high water wave hit the dock of the ocean where you have beach balls, the balls are thrown away and they are moving with greater kinetic energy. And when you have a lower amplitude, which means low intensity wave hitting the dock, this time the balls, the beach balls, are moving with lower kinetic energy. So according to, taking this analogy into photoelectric effect, which was explained by classical theory, it said a higher intensity light wave ejected electrons with higher kinetic energy, which means higher the intensity, more the energy of the ejected electrons. But again, practically, if the intensity of the light was increased, the electrons that ejected did not have higher kinetic energy. So this was second failure of wave theory in explaining photoelectric effect. Now the third one is the wave theory said that when the light falls on the metal surface, it will take some time to take up the energy from the photon, and then it will take some time to eject out of the plate. But practically, when this was done, there was no time lapse like that. As soon as the light fell, the electrons ejected instantaneously. So these are the three failures of wave theory or classical physics to explain photoelectric effect. So now we know the three failures of wave theory to explain the photoelectric effect. Now we will explain photoelectric effect using quantum theory or photon model. Okay, and this was used by Einstein. So here also I am taking analogy of the electrons and the light particles or the photons with the balls and bottles. So you can see there is a table. On that table you have balls, which we have a TT ball which have very low frequency. Then we have tennis ball, which is considered to be a photon of little higher frequency or energy, because energy is directly related to frequency. And then finally I have a cricket ball, which is supposed to have the highest frequency and highest energy. And the bottles are taken as the electrons on the metal plate, okay, a given metal plate. Now, let's see if you incident a very low frequency light, that is TT ball, and if it is made to fall on the metal plate, will it eject electron? So let's see. No, it does not, because it is a very low frequency light. It is not enough, the energy it possesses is not enough to eject the electron. Now let's try with a little higher frequency photon, which is taken to be the tennis ball. As you can see, it just topples the bottle, which means this is having frequency just enough to eject the electron from the metal plate. So this frequency is called threshold frequency, or the minimum frequency which will just eject the electron. Okay? Now let's try with the cricket ball, which is having higher frequency or higher energy. So now you see it hits the electrons. It is knocking the electron out of the metal surface with greater energy, which means if higher frequency light falls on a metal plate, then it will knock out the electron with greater energy. So from this analogy, what do you learn? First thing, there is a certain frequency above which only electrons are ejected, and the minimum frequency which ejects the electron is called threshold frequency. Another conclusion that can be made here is, if the frequency of the photon is high, then the electrons ejected will have higher kinetic energy. Okay, now what about intensity? What if you increase the intensity of the light? If you remember in my story, if the frequency increased, intensity increased, which was ultraviolet catastrophe. Now let's see here, what does it mean when we increase the intensity? Here, when I say I'm increasing the intensity, I am increasing the number of balls, which means number of photons. Okay, so let's try this again with higher intensity, which means more number of balls. Let's try whether the TT balls will throw away the bottles. It doesn't. Why? Because still it has lower frequency than the threshold frequency. Now let's try with the tennis ball. Let's increase the intensity, which means more number of balls. 3 balls ejected 3 electrons. Now what do you think would happen if you use cricket ball? Yes, if you use 3 cricket balls, it will knock out 3 electrons from the metal plate. So what does it mean? If you increase the intensity, the conclusion that you get from here, if you increase the intensity of the incident light, it will increase the number of electrons ejected from the plate. So higher the intensity, higher the number of photoelectrons ejected. So this was how photoelectric effect was explained by photon model, and this is how Einstein explained it. So from here, Einstein made photoelectric laws, so which states as follows. The first law says, for a given metal and frequency of incident radiation, the number of photoelectrons ejected per second is directly proportional to the intensity of the incident light. Number 2, for a given metal, there exists a certain minimum frequency called threshold frequency of the incident light, below which no emission of photoelectrons take place. Number 3, above the threshold frequency, the maximum kinetic energy of the emitted photoelectrons is independent of the intensity of light, but depends upon the frequency of the incident light. And number 4, the photoelectric emission is an instantaneous process. So these are the laws of photoelectric effect. Now comes photoelectric current. So photoelectric current, for that I have a diagram. You can see there is a kind of bulb up there from where the light is coming and falling on the metal plate. So when light falls on the metal plate, then it will eject electrons. Now, if you have another plate at the other end, which is called collector plate, and if it is given a positive terminal of the battery, then what happens? The electrons ejected will be attracted towards the positive plate because electrons are negative. So when that happens, then current starts to flow in this circuit. That current is called photoelectric current. Now, we will see in a simulation how this current will vary when you change the intensity and the frequency of the light. In this simulation, let's vary the intensity for a given frequency of light and see how the current, photoelectric current, changes. Okay? So now we have taken the metal plate as sodium, and then for now the intensity of the light is 0, and we have fixed the frequency of the light. Now let's see what happens if you increase the intensity. So now as we increase the intensity, you can see the number of electrons ejected from the sodium plates are increasing, and thereby current here you can see is also increasing. So which means with the increase in the amount of intensity of light, there is increase in current. The reading is here, and let's check in the graph also. So let's check in the graph. So you can see as the intensity is increased, in the graph also there is increase in the current. Not much, but there is. Okay, let us take another metal, just for instance, zinc. So in this metal, there is no flow of electrons, which means this metal plate requires more energy to eject electrons, which means it has a greater work function. Okay, now let's see how kinetic energy of the electron changes if you increase the frequency. So initially, let us take the frequency to be minimum. Let us take the intensity maximum. And again, we will take the sodium plate. Now we will slowly increase the frequency of the light, and let's see how the electrons are ejected. See, as the frequency increases, the electrons are ejecting, and as I increase the frequency, they are moving with greater speed, which indicates that they have greater kinetic energy. And you can see in the graph as well. So as the frequency increases, kinetic energy also increases of photoelectrons. So it's a positive graph. Okay, now there is one more thing that you will learn from here, which is new, which we didn't learn before. Suppose if I give a negative potential to the battery, which means now I am connecting this collector plate with negative terminal of the battery. So you know electrons and this negative terminal both are negative, so they will be repelling. So let's see what happens. So as I increase the frequency, kinetic energy of the electrons will be increasing, so they will come out. Now, till here, they do not have enough energy. They will be repelled. Now, if I increase the frequency, they will have enough energy to overcome that negative repulsion of the collector plate. So now the current is flowing. Now let me see if I increase the negative potential to 3. Still there is flow of electrons, which means there is flow of current. It means that the electrons have still some energy left to reach this plate. So now let me increase the negative potential further by -4 volt. Now you see that the electron do not have enough energy to reach the collector plate. As a result, there is no flow of current. See, current is 0. So this value of potential difference is called stopping potential or cutoff potential. So this makes the current stop. Now if you want to make the current flow again, what do you have to do? You have to increase the frequency so that the kinetic energy of the electron increases again and it reaches the metal plate. So as you can see, as I increase the frequency, current started to flow again. So this shows that stopping potential is directly proportional to frequency. So that is all from this simulation. Now we learn about the applications of photoelectric effect. See, we learned so much about photoelectric effect. Now where do we apply this? So we use photoelectric effect in solar panels. You see, sunlight will fall on the solar panel and this solar panel will eject electrons, and this electron will produce electricity which will be used to power up your house, make it hot, and run other electrical appliances. Now another appliance where this photoelectric effect is applied is CCD, Charge Coupled Device Sensor. This is a sensor you see in digital camera, modern digital camera. So this, what it does is actually when light falls, it captures the electrons and then in the form of pixel, and then it will be read digitally. So this is also applied here. Now, initial application was this photoelectric cell, where you have a cathode plate and an anode plate. So cathode plate is a photosensitive plate, and these two are kept in a evacuated tube. So here, high frequency light or light will fall on the sensitive plate and eject electron, which will be collected by the anode, and then outside in the circuit, current will flow. So this was the original one, and actually it looks like this photoelectric cell in reality. Nowadays, it is advanced, and it is called photodiodes, and it is advanced in a sense that it is incorporating semiconductors. So it is used in actually optic fiber telecommunication and also in solar cells. Now, these photo cells are further used in motion detectors, burglars alarm, traffic light controls, and automatic doors. So you can see there are lots of applications of photoelectric effect. Now, I want you to actually further find out more applications of photoelectric effect. Now, with this, we have come to the end of our lesson. So today, we learned about photoelectric effect, photon model of light, failure of wave theory to explain photoelectric effect, then laws of photoelectric effect, and applications of photoelectric effect. Now, I want you all to know further from my lesson. You can actually go through these questions and answer them so that you understand better. So the questions are, how does the change in the frequency of incident light affect the number of photoelectrons? You can answer this from the lesson. Number 2, metals such as sodium, lithium, and potassium shows photoelectric effect with visible light, whereas metals like zinc, magnesium, and cadmium need ultraviolet light to show photoelectric effect. Why? Now, the third one is, do you think particles have wave nature? Actually, you have this in your syllabus, so I want you to find yourselves if light can behave as wave as well as particle. Do you think particle will also behave as wave? So I hope you will try to find answer to these questions and explore more on your own. So with this, I close my lesson. Thank you for attending this lesson. I'll be seeing you all in my next lesson. Thank you.